Okay, the next rule is a rule that actually gets used quite a bit. Whenever I have some constant times whatever function comes next, it really does not matter. I could have had something like 5 and then using what we just did before, a sine of x dx. The key here is when I take the derivative of some constant times the function itself plus c, I can take the derivative of each part individually here. So I end up with, and that constant we can pull out, remember? And we did a nice little proof for that earlier in the year. So then it's a constant times the derivative of just f of x plus the derivative of c, which we know is equal to 0. And in this particular case, it ends up being k times the derivative of f of x, which ends up just being k times the derivative of f prime of x. But what this means is that if I reverse this process, it really means that this constant can be pulled out, which is the whole point of why I made sort of a separate one here. So this I could rewrite as k times the derivative of f prime of x dx, like that. And then it's just going to be k times f of x plus some constant. And even if I put parentheses around here, so I put a parenthesis around this one and I distributed the k, it just produces another constant c, so it really doesn't matter what this is. It does not get affected in the same way. So in this case, it just becomes k f of x plus c. So if I use this example right here, it would end up being, oh, that's the same as 5 times the antiderivative of sine of x dx. Oh, I'm running out of room here, which is equal to 5. And then the derivative of, the antiderivative of sine of x, we just figured out before, was negative cosine of x plus some constant, and then you can pull out the negative in front. So that's negative 5 cosine of x plus c. The sum and difference of functions, if I'm taking the derivative of the sum or the difference of two functions plus even a constant on the end, I can then separate them into 3 different parts, and I end up with just the derivative of the first function plus or minus the derivative of the second function plus 0, and we end up with the sum or the difference of their derivatives. What that means is then, in this particular case, I can actually do the same thing. I can separate them if I need to. So I could rewrite this as f prime of x dx plus minus g prime of x dx. Don't forget to distribute the dx, the variable of integration here. That's really important. Which then ends up being f of x plus minus g of x plus some constant. So it kind of stays the same throughout. There is a whole bunch of really good rules that you need to know. I've summarized a bunch of them in this particular fashion, but I'm not going to work through all of them. You can read through them. Some of them are pretty straightforward based on what you know about differentiation. So I think you guys will be in good shape, but you need to know them by heart. You need to know, you have got to have full mastery of all of these rules. Some techniques that will help you is that you need to rewrite equations if you can. So sometimes they become simpler using them with these rules. So if I looked at something like example 2 here, rewriting this so that I can use the power rule is actually really helpful. So I'm just like when we did derivatives. So I would rewrite this as x to the negative third dx, like that. And then I'm just going to use the power rule. So the power rule was, it's going to be, I'm going to have to add 1 to the exponent, and it's going to be 1 over one more than that, so that's negative 2. X to the negative second power plus some constant, which ends up equaling, let's clean it up. So maybe I would rewrite it as negative 1 over 2x squared plus c. That's prettier. For b, I would rewrite this one here, pull out the 2 like we just did before, sine of x dx, and then you take the derivative, so it's going to be negative 2 cosine of x plus c. Don't forget the c. This one here, rewrite into 2 terms. Don't forget this is x to the 1/2, so, and then bring it up. So we can rewrite, before I even do the integration, it's going to be x to the 1/2 plus x to the negative 1/2 in parentheses dx, because the dx is the variable for both parts. And then you can do each part separately. You don't have to rewrite them separately. I'm just doing it for illustration purposes, but you can do that in your head if you wanted to. But it would be rewritten like this. Oops, negative 1/2 dx, and again the dx distributes to both of them, and then using the power rule, I know that it's going to be 1 over, and then add 1 to this exponent, which is 3 over 2, x 3 over 2, plus some constant, which is okay, because I'm going to add another constant, so it just gives me one big constant for the whole thing, plus 1 over, add 1 to here, gives me 1/2, x to the 1/2, and here's the constant, and the constant from this one and the constant from that one just adds up to another constant, so it doesn't really matter. So in this particular case, we're going to clean it up a little bit. You don't write a fraction within a fraction, so this becomes 2/3. The reciprocal, this is like saying the reciprocal of 3 over 2, which is 2/3, x to the 3/2 plus 2, x to the 1/2 plus c. And when we get into trig functions, really helpful to rewrite. Remember your trig identities. I know it's your favorite. I see sine over cosine, just to illustrate. And again, you don't have to rewrite it, all of these steps over and over again, but I'm just showing you I could rewrite it like this, dx, which then becomes tangent of x times, oh, I forgot secant, whoops, secant of x dx. And if you don't remember which derivative ended up with this, just for now, I have put a whole bunch of references on the next couple of sheets. So if you go to the next page, all of the trig functions, you see this one here, secant of x times tangent of x. Well, that was the derivative of secant of x. But if you didn't remember that, I put all of the references. These you need to know. You just have to know them. So in this case, it's going to be secant of x plus c. Most important rules, there are a few others we're going to add and subtract later on, but they're coming on the next 2 pages. I did sort of the explanation on the sides because of the derivative here, but here on the left-hand side are the actual rules. This one we already did. Exponential functions is kind of a fun one. You guys should know, the derivative of e to the x is e to the x, so when you take the antiderivative of it, it's also going to be e to the x, which is so cool to me. Also the reciprocal functions, which is kind of an interesting one. All the trig functions here. The inverse trig functions, ouch, those are harder to remember sometimes. It's kind of interesting because tangent, the inverse trig functions, so the arctangent and the negative of arccotangent are actually, can be named for either one of them. Most often we use tangent, but just be aware. And the same here, sine and the negative, arcsine and the negative of arccosine actually has the same derivative. So that means when we take the antiderivative, it could be either one. Okie doke. Now I want you guys to try these problems. It's just the rewrite like we just did before on your own. And I'll give you the answers in the next video. And please make sure you try and answer this one. It's so important, and it's a big star here next to this. Super important that you remember, if it's indefinite, to add the C.